Okay, we're going to venture into probability in this chapter, but before we do, we need to talk about sets and Venn diagrams. Now, this may or may not be covered in a college algebra course, so I'm going to go ahead and include it since it's in most college algebra books. But we definitely cover this material in a finite math course and also in statistics. So it might help you down the road at any rate. So let's talk about a set. A set is any collection of objects or elements written in such a way that we can tell whether any given object is in the set or not in the set. Now, we use uppercase letters like capital A, B, and C to represent sets. And the objects in the sets are called elements or members, and we generally would use lowercase letters for elements in the set. Or we might just, whatever the elements are, use that to represent them. So let's talk a little bit about notation. Little a, and this symbol here means is an element of capital A. So that basically means whatever little a is, it's in the set capital A. And this just means little a is not an element of the set capital A. So for example, if I consider the counting numbers 1 through 9, and let's say I'm going to say set A are the numbers 2, 3, 5, 6, 8, 9, then 2 would be an element of A, capital A, because 2 is in the set, and 1 would not be an element of A because 1 is not in the set A. Now, an empty set, a set with no elements in it, is called an empty set. And there's a couple of notations you can use. You can use the null symbol, or you can use just a set of empty braces. So that both of those represent the empty set. So, for example, consider all numbers rolled on a six-sided die. So if I said the list of those numbers, those would be the numbers 1 through 6. Well, if I asked you to list the numbers that are rolled on a die that are greater than 10, well, after you looked at me kind of strange, you would say that that is the empty set because there's no elements in that set. There's no elements that are greater, there's no numbers greater than 10 that fall within this set. So that would be the empty sets. Now some other set symbols, this symbol here means set A is a subset of B. That just means every element that's in A is also in set B. Now if you have A equals B, that means the two sets are exactly the same. That means that every element that's in set A is in B, and every element that's in set B is also in A. So in other words, A would be a subset of B, and B would be a subset of A. Now, this just means A is not a subset of B, and this just means that A, set A, does not equal set B. So some examples here, go back to our counting numbers 1 through 9. So let's say A is the odd numbers 1, 3, 5, 7, 9. B are the even numbers 2, 4, 6, 8. C is the set with the two numbers 3 and 5, and D is the set 2, 4, 6, 8. So we could say that C is a subset of A because everything that's in C is also in A. We would say that C is not a subset of B because there are elements in C that are not in B. We could say that A, let's see, we could say that, let's see, could we say A is, no, we can't say A equals D, can we? We can say that A does not equal D, right? Because A and D are not the same sets. We could say that A does not equal B, right? Because A and B are not the same sets. And we could say that A does not equal C. I don't really have a set where I can say that A equals that, but anyway, I would just basically write the same set if I did. Okay. Now the empty set is a subset of every set. So the empty set is a subset of set A, set B, and set C, and so on. Now, let's talk about the universal set and Venn diagrams. The universal set U, not to be confused with the union symbol, is the set that represents all elements that are being considered. A Venn diagram is a visual representation of one or more sets. And I'm going to show you the Venn diagram for the union of sets A and B in a moment. Okay, so consider the counting numbers 1 through 9. then we would consider the universal set to be all those numbers 1 through 9. That would be the universal set. Okay? Now, let's talk about the union of two sets. The union of two sets, A and B, denoted by this symbol A union B, is the set of all elements formed by combining all elements of set A with all elements set B into one set. But we don't include an element twice. So make sure you don't confuse the universal set U with the notation for union. Okay, so let's look at an example. Okay, so let's go back to our universal set 1 through 9. So that's going to be our universal set. Okay, now I've identified these three sets. A is 1, 3, 5, 7, 9, B is 3, 4, 5, 6, and C is 2, 4, 6, 8. Well, A union B would be everything that's in A plus everything that's in B. So I would include 1, 3, 4, 5, 6, 7, and 9. But notice I only include the elements once. So even though 3 occurs in both sets, I don't write it twice. I just write it once. Now A union C would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So A union C is basically everything that's in the universal set. And then if we talked about the intersection of two sets, the intersection of two sets, A and B, denoted by this symbol, A intersect B, is the set of all elements formed by listing all the elements that simultaneously occur in both sets. So let's use our same universal set again, and let's look at the sets A and B. Well, A intersect B, well, notice that 3 is in set A and it's in set B, so it's in the intersection. 5 is in set A and it's in set B, so that's in the intersection. So those are the only elements that are in both sets. Now, sometimes the intersection could be empty. So if you look at set A and you look at set C, you can see that there are no elements that fall in A and C simultaneously. So in that case, we would say that A intersects C is the empty set. Would B intersect C be empty? Let's see. B intersects C, well, 4 and 6, that would be the intersection there, right? So B intersects C would be the numbers 4 and 6. So B intersects C is not empty. Okay, now Venn diagrams are helpful in looking at sets. So let me show you, when we do a Venn diagram, we generally draw a rectangle around the entire group, and everything in the rectangle represents the universal set. In other words, the set of all elements. Now, if you look at these two symbols here, this set is set A. The first circle is set A. The second circle is set B. Notice that I've shaded everything in A and everything in B. Well, basically, that means that set A plus set B, that represents the union. So everything shaded there is the union. Now, but when you're representing the intersection of two sets, you're actually looking where they overlap. So if you'll notice here, I've got set A on the left, set B on the right, but in the middle, I have a darker region, a darker purple region here, and that's actually represents the intersection of sets A and B. And these diagrams came from, or images came off of Wikipedia. Okay, now the complement of a set is the complement of set A, denoted by A prime. It can also be written in some books, they might use an A with a little bar across it. But anyway, this is the set of elements in the universal set that are not in A. So let's go back and consider our universal set, the numbers 1 through 9. Well, if A is the set 1, 3, 5, 7, 9, then A prime, or not A, would be the elements that are in the universal set that are not in A. So what did we leave out here? We left out 2, 4, 6, 8. What about B prime? Well, if B is 3, 4, 5, 6, then B prime would be everything that's not in this set, but that is in the universal set. So it would be the numbers 1, 2, 7, 8, and 9. Now the Venn diagram for the complement is you really just need set A. Notice this red circle, that represents everything that's in set A. So basically, if I did a diagram here, set A, I can't really, hang on, let me do it this way because the color won't show up. Let me change colors. Okay, so using the example I used up here, notice in set A it contains the elements 1, 3, 5, 7, 9. And then outside of A, this green region is A prime. And A prime contains the other values 2, 4, 6, and 8. So that's how it works visually. Okay, let's look at an application. So if a poll was passed out to 100 students and it had 3 questions and it said, do you own an iPad, do you own a laptop, or do you own an iPad and a laptop? Well, 70 of the students said yes to the first question, so that means 30 said no. 50 of the students said yes to the second question, so that means 50 of the students said no. And then 40 said yes to the third question, so 40 said they own both, so that means 60 said no. So if I said now, how many students own an iPad but do not own a laptop, or how many own a laptop but not an iPad, or how many own an iPad or laptop, or how many own an iPad nor laptop, or how many do not own an iPad, well, this is where Venn diagrams can be very helpful. So if you look at the example of this Venn diagram, and let me make it fit the screen here for us. Okay, so if you look at the example of this Venn diagram, well, the universal set has 100 because 100 students were polled. And this is set A. I left off the A. Okay, so this is set A. This would be the students that said yes to an iPad. So remember, we said 70 said yes to an iPad, right? So this circle would be all the students that own iPads. And this circle has to contain 70 students. This other circle is B. This is those that own a laptop. Well, 50 said yes to that, so this circle has to have 50 in it. But then you might remember that 40 said yes to both. So there's 40 inside here. Well, if there's 40 in here, if there's 40 that own an iPad and a laptop, then that means that there must be 30 here that own an iPad but do not own a laptop. So that, and how did I get that? I took the total of 70 that's in this A circle and I subtracted the 40 and got 30. And now over here, if I want to know how many are going to be out here, the ones that don't own an iPad but they own a laptop, then I take the 50 minus 40 and I get the 10. And then if you add these up, you get 30 plus 40 plus 10. That adds up to a total of 80. And those 3 sets don't intersect. And if you subtract 80 from 100, you actually get 20 out here that own neither. So once you get all of these areas filled out, once you get this area filled out at 30, this area with 40, and this area with 10, and then the outside area with 20, then you can answer all of the questions. So the first question says, how many owns an iPad but not a laptop? Well, that's A intersect not B. So that answer would be 30. And then how many students own a laptop but not on an iPad? That's A prime intersect B, and that answer is 10. And then it says how many own neither? Well, that answer would be the 80. Let's see, how many own neither an iPad? Oh, either. That would be 80. So you add the 3, 30, 40, and 10 together to get 80. And then neither would be 20. So you take the 80 away from 100 and get 20 that own neither. And this last one's a little tricky. How many do not own an iPad? Well, the iPad circle would be these people in here. So somebody might say 10 is the answer. But you got to remember that these guys on the outside don't own an iPad either. So it's actually these 10 plus these 20, and so you get 30. And so that's all we have. I'll finish this section on the next video because that's all I have time for on this one.